Welcome to Finite Element Methods. We'll be discussing the frequency in model extraction. It's a dynamic characterization procedure to understand the dynamics of a system. And here what I'm going to do, I'm going to talk about the Tacoma Bridge, which collapsed due to a flutter event. So let's look at this video really quick. And what we're going to see is a resonant vibration of the bridge in a torsional mode. In this case, the Tacoma Narrows Bridge collapsed as it experienced winds of about 19 meters per second, close to 70 kilometers per hour. The center state was torsionally vibrating at a frequency of quite a bit in 9 different segments. And over the next hour, the torsional vibration amplitude built up and the motion had changed from rhythmically rising and falling to two-wave twisting, as you can see. Despite all this motion, the center part of the bridge was motionless, while other two halves continued to twist in opposite directions. What we notice here is that there's a drastic torsional motion, which was started by a failure of a cable, and that basically increased in size. These amplitudes increased in size until cracks developed and the entire bridge crashed over. Very, very powerful event that demonstrates how wind can couple with frequencies and dynamics of the bridge. And when they coupled, it can cause a resonant condition. And in this case, what people have found is that wind-induced oscillations can occur and can be quite dramatic. There's been wind tunnel test experiments on this that usually can have explained this type of failure. And this is what we call an aerodynamically unstable event. And this is not a new problem. It's occurred in other types of structures, but at the time, this factor was not considered here. So what is the physics? Is that you really have these vortex events that have frequency and that occurred at a certain frequencies or cycles per second. And the bridge will have a dynamic characteristic that can be described in terms of frequencies and mode shapes. And in essence, what we're talking about is the natural vibration of the structure due to vibration. Let's talk about the dynamic analysis. So we'll be discussing the transient dynamic analysis, but we're going to look at other methods of doing it because what we had discussed was the transient dynamic analysis with direct time integration. That's the very previous lecture. We can discretize the spatial domain using finite elements and integrate the equation of motions directly from some sort of low time history. And I demonstrated that using the Newmark beta method. We can solve for deflections, velocities, stresses as a function of time. The benefits of this approach is that it predicts the structural behavior due to time varying excitation. The transient load excitation is explicitly defined in the time domain. It allows definition of applied forces and or reinforced motions and can be modeled nonlinear. It can model a nonlinear behavior such as contact and plasticity. For example, a million degree of freedom finite element model will need to be solved for all variables of interest at every time step. That's what we saw. So if I have a million degrees of freedom structure, I'm going to have to solve for all those variables as a function of time. And that can be quite expensive, computationally expensive. For a linear system, it may be more advantageous to solve the problem using model dynamics. But before I can tackle that, we really need to understand the idea of frequency model analysis. The frequency model analysis is a free vibration eigenvalue problem, and it allows us to determine the natural frequencies and normal modes. And then we can determine the transient response, and I'll discuss that later. We can actually determine the transient response using these normal modes. The motivation for free vibration problems is that it allows us to verify stiffness requirements. You may want to stay away from certain frequencies. And so you could use that. Model identification and correlation to test. So you have a model, representative model of the physical system, and you want to determine whether dynamics of that model correlate well with the testing. To assess the dynamic interaction with another structural component. So I want to make sure that I don't have this coupling effect that we just saw in the bridge example. And we want to make sure we don't have a problem that, say, the frequencies of the forcing function coupled with the fundamental frequencies of the structure, and that in turn causes a resonant condition that can cause failure. It can also be used to evaluate design change evaluation. So for example, you can look at the frequencies to see if design changes had any effects on them. And one of the most fundamental ideas here is to use this free vibration or modal dynamic characterization, this frequency and mode shift characterization, which I'll discuss a little bit later, to understand the transient response. And that will simplify greatly the analysis. We also want to ensure that we can detect events that could look like that could look like a resonant condition that could lead to a failure, such as the Tacoma bridge failure. It can also be used for damage detection. So say you have a sensors across a system that measure the vibration. If there was a delamination or a crack, you'll expect some stiffness degradation. And that stiffness degradation could mean that I have a change in frequency. That shift in frequency can tell us quite a bit about a potential of the existence of a crack. So very interesting idea here that actually is quite important in structural dynamics and can be very useful application. So that's really good what we've accomplished there. And the other thing I want to make sure is understood is that every structure is going to have natural mode shapes and natural frequencies. You can have natural frequencies and then associated mode shapes with those frequencies. Here, what you see is a plate that's simply supported around the four edges. And around these four edges, we simply support it. And then what you see here is the different modes. And what are modes? Modes are basically shapes that the structure is taking. You can see those here. You can see some sort of shape that's very simple. Here you have a double half sine wave, as you can see, a single sine wave, as you can see, in multiple directions. But it is taking some shapes here. So what you see here at the top are the frequencies. And what is this? So natural frequency, these are the natural frequencies. So what is a natural frequency? And it's also known as eigenfrequency. I'll explain that a little bit later. Natural frequency is the frequency at which a system will tend to oscillate in the absence of a damping or force. The motion pattern of a system oscillating at this natural frequency is called a normal mode. So if I were to have a frequency of this kind, of this amount, I will expect a mode shape or a motion pattern that looks like this. And you're going to have the greatest motion when the forcing frequency, if I have an external forcing frequency for that matches the frequency at this of this plate. At say I have a forcing function with a frequency of 12.1674, you could have a resonant condition, for example. And so typically frequency is basically cycles per second. So for every second, how many cycles do I get? And here what we're saying is that we have 12.16 cycles per second. So this is telling us a lot about the information of the system relative to the frequency and the mode shapes. One thing I want to point out is that these mode shapes are arbitrary in nature. We know what the shape is. We don't know if what the amplitude really is. We can determine that with a different kind of analysis, but this analysis will only tell us what are the natural frequencies and what kinds of mode shapes or patterns, deformation patterns the structure will take at that particular vibrating frequency in the absence of dynamic damping forces. These mode shapes are arbitrary in nature. And I call this information the DNA of every structure. So every structure has a particular DNA, and the natural frequencies and mode shapes allows us to understand and fully characterize that system. And it can be unique per system. And so that's a very interesting idea that becomes very important. And I'll show you later how that could be important. But one of the ways that this could be important is that if I have a forcing frequency of 12.1674, I want to make sure that I don't have a resonant condition against this plate. So one thing I could do is redesign this plate so that I try to stay away from that forcing frequency, for example. Another approach is to modify the forcing frequency so it doesn't match the period of vibration that I have here in this example. So what drives the natural frequency of mode shapes? What fundamental parameters can drive that? They could be geometry, for example. It could be the boundary conditions. So if this end was free, then the period of vibration will change. Stiffness, mass, all those are quantities that can drive the natural frequencies and mode shapes of the system. Very important idea that's going to become quite fundamental later on as I work through the problems for transient analysis. And what we're trying to accomplish is really reduce the computational time when we do transient analysis if we were to have a linear response. So how do I determine the mode shapes and frequencies analytically? So we'll have to go back and study for example, let's choose the clamped beam, a clamped beam, and I want to determine what are the mode shapes and natural frequencies of the system. So this is the equations of motion for a beam. E is the modulus, I is the inertia, W is the transverse deflection, rho is the density, A is the cross-sectional area, and T is time. So what I want to do, I'm going to substitute a deflection that's equal to this amplitude, W, which varies spatially across the beam, times a harmonic function, which I'm going to call EI omega t. If I plug this into this equation, you will find that what I get here is EI omega t again, but now I have this W here, which is only a function of X. So this is allowing us a separation of variable approach. You can see here that when I find the second derivative of this, the secondary derivative EI omega t results in minus omega squared W of X EI omega t. And then this rho A goes here. I could cancel EI omega t since that's not equal to 0. There's no way EI omega t can be 0. And that gives me this equation. And what I want to do is I want to divide this whole thing by EI so it looks very compact in this manner. And so this is a fourth order differential equation. I can call this lambda here, which now depends on omega squared, the density, the cross-sectional area, the modulus, and the moment of inertia. So we'll assume deflection of this form. So we'll assume this equation here at the bottom. And what you see here is that it depends on, has 4 coefficients that are unknown. How do I find them? Well, if I were to have a cantilever beam where the left-hand side is clamped and the right-hand side is free, on the left-hand side, the deflection is 0. The slope is 0 because it's clamped. On the right-hand side, the moment is 0 and the shear is 0. So I have these conditions here that I can now apply to this displacement solution to determine C1, C2, C3, and C4. And that's for this particular example. When I do that, I will find that I have these 4 equations here, right? Because I'm imposing these 4 boundary conditions to this displacement solution. And I want to find C1, C2, C3, and C4. So when I do that, the trivial solution is that C1 and C2 and C3 and C4 is 0, but the non-trivial solution is such that the determinant of this matrix is equal to 0. And so what I find when I find the determinant of this system is that I have basically an eigenvalue problem. And the characteristic equation that comes out of this determinant is cosine lambda L cosh lambda L, hyperbolic cosine, equals -1. And there's multiple solutions that stem out of this equation. These are the solutions you get: lambda L1, lambda L2, and so forth. So there's many of them. There's infinite number of eigenvalues. So for a free cantilever beam, I'm ready to calculate the frequencies, the eigenfrequencies, and this is what I get. And F equals omega I over 2 pi, and that puts in terms of hertz, which is cycles per second. So what you see here is that I know I know lambda L because that's these different eigen solutions, and I have different omegas, infinite number of them as a consequence. EI rho A L to the fourth, all this is known for a particular beam. So you can calculate the frequency or the circular frequency very easily. So with this information now, I'm ready to determine what the mode shapes could be. You can also determine the mode shapes. And in these examples, I showed you that can calculate the mode shapes very readily. But how do I approach this? So again, there's infinite number of mode shapes with corresponding frequencies. And what I do now to try to determine a systematic approach to try to find these eigenfrequencies. Well, doing it by hand will be intractable for an aircraft. So we want to recur back to the Wick from Galerkin approaches that we have previously discussed. Here, what I've done is I'm going to start with the Wick from Galerkin I had shown previously. I've shown this before. This is what we derived in the previous lecture. And all we've done is formulated the residual using this equation. But now we don't have the distributed forces because it's a free vibration problem. We don't have the distributed forces applied. So normally when you're trying to find modal frequencies and natural frequencies, you're not applying a force to determine, you don't have a forcing function applied to it. You're trying to find the free modes of vibration. So I don't have the distributed load here. This Q is not here, but and I'm not going to apply any forces at the boundaries. First of all, the boundary conditions at x equals 0 are such that v at 0 is 0, v at L is 0. So sorry, not v at 0. V at 0 is 0, v prime at 0 is 0. But the shear and the moment are also 0. So this whole thing vanishes, and I get this equation right here. So very simple equation, no distributed load, no forcing functions applied because I'm looking at the free vibration problem. And then the boundary conditions are such that all these boundaries disappear because I have a clamped condition. If I want to examine a simply supported condition, for example, where it's pinned, then V at 0 is 0, V at L is 0, so this goes away. And then I have no moments applied, so this is also 0. So it doesn't matter what you do in a free vibration problem, you're going to end up with an equation that looks like this. Very simple equation. And so that's the Wick from Galerkin. And I've derived that in the previous lecture, and that's why I'm not doing it again. And notice how I can now use separation variables. What I'll do is W tilde, the approximation function, will be equal to separation variables that we'll be using. And bold contains, is only a function of x. And it contains a shape function. Phi are the nodal coordinates. So if I have an element at the nodal coordinates become the deflection and the slope at each node. And so that's what goes here for Euler Bernoulli beam, remember? And then I have EI omega t. So I'm going to assume a harmonic motion. W tilde double prime, basically just that derivative is respect to x only, so it only applies to m bold. Phi contains a nodal unknowns, so nothing to be applied here. And then in ei omega t, this is b bold, and then I have phi ei omega t, and then the second derivative of w tilde with respect to time is minus omega squared m bold phi bold ei omega t. And so that's because the second derivative of w respect to t time is only applied to the ei omega t, and so that just results in this. And then anywhere I see v, I'll put it as m bold t transpose. But I have a second derivative here that I need to take. So that'll become b bold transpose when I put it in there. And so let's see what we got. We plug in the following approximations. I had to calculate this. And so I'll just plug it in. We just plug in these expressions. So this expression goes in here. This expression goes in there. That becomes B bold transpose. This expression goes in there. When I do all those plugins, EI omega T factors out. And phi bold also factors out. You can see that here. And then omega squared does not depend on dx, so that can be factored out in this manner. And notice how this is stiffness matrix and this is a mass matrix. And note again here that phi is not a function of time. These are the nodal coordinates of the nodal coordinates and the nodal values that I don't know about. And notice that here phi is not a function of time and does represent the shape of the system. Okay, so the only thing now, that's the difference between what we did in the previous lecture, where I separated the variables. So it was w tilde x comma t, m bold time a coefficient, nodal unknowns, which also depend on time. Here, I have taken phi bold and made it independent of ei omega t of time by doing these separation variables. Now, phi bold does not depend on time. Big distinction between what we did before in the transient analysis versus what I'm doing here. So phi bold, again, this is no dependence on time and no spatial dependence either, because the spatial dependence is taken care by the shape functions. The Hermitian cubic polynomials go here, and then phi bold is just nodal values that don't depend on time, because I separated the variables further and made an assumption that the behavior is harmonic. As a consequence, ei omega t can be canceled since that will never be equal to 0. And I get this equation. So if I calculate these integrals here, which I did for the previous lecture, I get this right here. And if I plug it in for single element, this is what I get. And phi is this column vector. Now notice in a transient solution, this also depends of time. But again, I decouple it further by assuming a harmonic solution here. So for a single element, this is what I get. If you had more than one element, you can assemble the whole thing together and get a bigger matrix. But this is what I have now. Since this is a clamped boundary condition, we can then apply this to be 0 and this is 0. And so these equations reduce to the bottom two equations. So I can look at these two equations. And what I notice here is that I'll find a quadratic equation on omega squared. And there's only really two eigenvalue solutions to the problem. So, and how do I find a quadratic equation? Is by setting this determinant equal to 0. And that will allow me to find the eigenfrequencies and corresponding Modeshapes of the system. If I assume E is aluminum, A is 1 inch squared, L is 20, I is this much, rho is this much, I can plug all that in to get this equation right here. So we can now use the quadratic equation and we can solve, by the way, Mathematica or MATLAB can find the eigenvalues. We can solve the equation stemming from this determinant, which will then give eigenvalues that look like this. So omega squared is this, so the frequency is 81 hertz. And then here I have 784 hertz. So those are the mode shapes. And what that's telling me is that the system will vibrate at 81 cycles per second. That's the first frequency. The second frequency is 794 hertz, which is telling us that the system or the beam will vibrate at 784 cycles per second. So how do I determine the mode shape? So once you determine omega squared, you can then determine the mode shapes. You can plug in this right here, this 2.56 10 to the 5 into this equation. And once I do that, I can calculate V2 and theta 2. You can solve V2 in terms of theta 2. And you'll find the eigenvector, which this is what you get for the first mode shape. For the second mode shape, you can do the same thing. So plug in this equation in here. Sorry, you plug in this equation in here, which is, and then you can do the same thing. Solve V2 in terms of theta 2, and then you get this arbitrary mode shape. Again, it's arbitrary because V2 depends on theta 2, so you can scale it to whatever number you want. I invite you to do it so you can see for yourself that there's infinite number of pairs of V2 and theta 2 that satisfy this equation, but there's only one way to make this work, which is there's a factor of V2 that relates to theta 2. If I were to plot the mode shapes corresponding to 81 hertz, what I find is I have this 0 and 0 because the nodal values in the node I, in the first node, is 0 since it's clamped. And then for the second node, I found that these were the deflections. So I can put it here and I can multiply m bold times this in order to plot the deflection W tilde. And when I do that, that looks like bending of that beam. And what this is telling me is that this beam will oscillate back and forth in this shape at 81 hertz, at 81 cycles per second, if it were to vibrate at this frequency. The mode shapes at 794 hertz look a little more complicated. You have this like just a more complicated bending scenario, or secondary bending almost. And what this is telling us is that at 794 cycles per second, the system will oscillate in this shape. It's more likely to oscillate in this shape. In real systems, very likely the system will oscillate, so it's a combination of these two, right? So very interesting. I told you earlier how the analytical solution, this analytical solution right here, has infinite number of eigenvalues. But because I discretized the domain into one element, I ended up in this case with two eigenvalues corresponding to two eigenmodes because I only have 2 degrees of freedom. So a system with n degrees of freedom will have n eigenfrequencies corresponding to n eigenmodes. Now that's in contrast to a continuous system that if it were to have in a continuous system, you will have infinite number of eigenfrequencies and mode shapes. The eigenmodes have arbitrary amplitude. Its amplitude is not known, only its shape. And the dynamic characteristics of the system are defined by these eigenmodes and frequencies. If I were to have a 20 element clamped beam, so for a 20 element system that's clamped, each element will be 1 inch long, and there will be 40 degrees of freedom in this case. For this system, we calculate 40 eigenfrequencies and 40 eigenmodes. The assembly of the stiffness matrix and mass matrix can then be determined by using the element connectivity matrix. So when I assemble a 20, and I did it, when I assemble 20 elements, this is what I get. And then I can use Mathematica or MATLAB to determine the eigenfrequencies and eigenmode shapes. So and I will have a lot of frequencies and mode shapes to look at. For one element, we got 81 hertz and 794 hertz using Mathematica. For 20 elements, notice how I got 81 hertz and 502 hertz. Obviously, the first one looks pretty good. The second one, for one element versus 20 elements, is quite off. Obviously, one element will have a hard time representing the behavior correctly. But 20 elements, this is what we got. And I have many more frequencies than that, but I'm showing the top 6. The analytical frequency using the closed form solution is 8506, and you can see how the 20 element solution does really well all the way to 6 modes. There's many more modes, but I'm showing you some of them. You will find that the solution matches the analytical solutions really well. How will you determine the mode shapes and frequencies, natural frequencies, using Abacus? How do you extract that information from a model? Because that's very important in design to determine that. So how do you do that? First, I recommend providing the node information, then the element definition. We're going to use the Euler-Bernoulli beam theory here. And then I'm not showing all the elements definition here. Then I provide the beam cross-section information, which is a 1-inch squared area, the elastic modulus, Poisson ratio, and density. You then going to extract, here I'm extracting 50 frequencies, and I'm clamping the left-hand side here. So what are the mode shapes and frequencies using Abacus? I can plot them very easily. 81 hertz looks like that. That's the first mode shape. And what is that first mode shape? That mode shape is such that it looks like bending and is going to oscillate at 81 hertz in that shape, back and forth, 81 cycles per second. The second mode shape looks a lot more complex, and it's going to take that shape if you were to vibrate at 502 hertz. The third mode shape looks even more complicated. The fifth mode shape looks like this, the sixth mode like that, and the seventh mode like that, and it gets more and more complex. You're going to have more half sine waves, and you will see that Abacus produces an axial mode, which the formulation we have here did not include the ability to actually deform, but the one in Abacus does, and that's why it produces this axial mode here. And if we were to include that in our formulation, we'll get the same thing. So how does Abacus compare to Mathematica and Analytical solution? You can see that the Mathematica solution matches exactly the Abacus solution, and it's pretty close to the Analytical solution. So in this lecture, what we've learned is a very important consideration, is that when we study dynamics, it's very, very useful to understand the dynamic characteristics of that structure, and how we characterize the dynamics, that DNA of that structure, is to understand the natural frequencies and corresponding mode shapes. And what is a natural frequency? If it's basically a free vibration problem, and if I were to, with no damping and no forcing frequency, what I want to understand is if the structure were to vibrate, and it vibrated at that frequency, what shape does it take? And what frequency is more likely to vibrate at? You can see here, these are the fundamental frequencies. This is the fundamental frequency, and you have natural frequencies at which that structure could vibrate. And it will take that motion if it did. And this number represents the number of cycles per second that will happen. So it will have a cycle, there'll be 26.57 cycles, 26.57 cycles per second of this oscillation of this shape. And how is this important? It helps us, again, to make sure that I can design a system that doesn't enter into resonance against something else. I can use it for damage detection. If I put a crack here, for example, the stiffness will change. So I know that something happened to the structure, and I can study that frequency shift. Can be used for transient response analysis, can be used to look at design change evaluation. And I'm going to be looking at transient response analysis coming up in the next lecture. But the point was to demonstrate why is this useful? Why is this used? Another powerful way I'll show later is, say I have a structure that's tested to determine the model frequencies and natural frequencies. If I were to develop a model of that, I could then correlate the analysis to the test using something called the model correlation. And I'll discuss that later. But this is very important. This is very useful information, and it's very, very powerful. So with that said, I thank you for listening to this lecture and have a great day.